So welcome everybody to this webinar on designing and of wearable antennas. Today's seminar is presented by myself. My name is Amar Kuki. I'm with HFWorks, Senior Application Engineer. And what we'd like to do today is really go over this brief introduction about this, how we do the simulation and the design of antennas using our products. And we will show you software in action, so you can see how this is done and see some of the parameters we're looking for in terms of antenna performance and so on. And then we'll have Q&A session at the end if time allows. So we'd like to do this quickly so that we don't want to keep you longer than necessary. So some initial housekeeping notes. So if you guys have any questions at any given time, if you look at your GoToMeeting interface, there is a section for chat. You can just type in your message and make sure that it's sent to the organizers or to everyone attending. And we will try to monitor this as we go along and answer questions as they arise. So if you have a question in the process and we see that it, it helps to go over that specific question during the presentation, we'll do it. Otherwise, we'll go at the end of the session and see all the questions and try to answer them. So by way of introduction, I think today's wearable electronics are witnessing a big increase, a big evolution in the market. And if you look at any recent studies, this is a market that's really taking off very fast. And you see a wide variety of devices and so on that are coming into the market. For sure, at least in the US, market, already 20% of the population have some kind of wearable electronics. So this is really a very, very important and growing industry. This industry, the requirements is obviously, as many modern electronics, we need them to be wireless. And so the fact of being wireless, basically leads us to antenna considerations. How to make these antennas and how do we meet requirements for the system operation with a well-designed antenna, and how do we actually go about designing such antennas and so on. So that is really what we are trying to show you today, is that using our software, we'll be able to address and answer some of these questions. So if you think about the wireless wearables, and we are today focusing on antennas, then the antennas, there are different antenna parameters that one needs to consider, and these include, obviously, you can have polarization consideration, obviously the input and impedance of the antenna, its efficiency, its gain, and the radiation pattern. And not all of these parameters are independent, but these are important antenna parameters that you look for. And you have to design these antennas subject usually to certain considerations. You might have size considerations, you might have shape requirements, where to be with the placement, what kind of coverage you want to obtain with this antenna, and what kind of materials you can play with and see if it performs, and a whole number of other issues that can be of relevance to the designer and the product developer. And so to illustrate how we do this, we believe that we have a very compelling solution, because we offer a SOLIDWORKS HFWorks combination to address these issues and all other kind of electromagnetic design issues. So what we're offering is really this unique combination where we are leveraging the power of SOLIDWORKS as being the CAD platform on which the geometry gets created, the model gets built, SOLIDWORKS is a leading 3D CAD package in the world. It's very easy to use, so we can build geometries quickly and easily. If you want to make changes to geometry, it's relatively straightforward. It's really easy. And it has one of the key issues that we would like to highlight today is the ability within a single design to investigate different configurations and explore alternative designs. So so this is the power of CAD. The HFWorks product that we'll be highlighting today is our 3D full wave EM simulator, which is a product of HFWorks. SOLIDWORKS is a product of the SOLIDWORKS Corporation. So our HFWorks package is one of our two flagship products. This particular product is destined to the high frequency microwave, wireless, millimeter wave markets. It is fully embedded inside SOLIDWORKS, as you will see shortly. It is also gold certified by SOLIDWORKS Corporation, which means that it respects stringent rules of integration within SOLIDWORKS. And it also has a whole host of features, and one of the key things that designers should be aware of is that it also does electrothermal and electrothermal structural simulation. So if, in cases where power is an issue and thermal heating and so on is also an issue, then we can do that as well. And this could be relevant also to wearable electronics if you wanted to see how much of the radiation penetrates the body and how much it heats up and so on. So those are accessible. So although we'll not go over these things today specifically, but you should know that it's available within the HFWorks package. And being embedded inside SOLIDWORKS, it also allows us to do the electromagnetic investigation of alternative designs in an efficient manner. So we can use the alternative configurations that we build inside SOLIDWORKS, or we can parameterize dimensions or other parameters in the simulation and explore our design space in that manner. So today's model, what we're working, what we'll be focusing on is really the design of a Bluetooth antenna that will operate at the ISM band at 2.45 gigahertz. Coverage-wise, we would like to have an omnidirectional antenna because we don't know in which direction the transmitter and the receiver might be related to each other. We'd like it to have linear polarization, and ideally we'd like it to have 50 ohm input impedance and be with it well matched around the 2.45 gigahertz band. Ideally it should be small to fit in bracelet type of wearables. So a size dimension of around 8 by 9 by 0.15 millimeters, so quite thin, and less than 1 centimeter by 1 centimeter, and we want it to be obviously a printable antenna, so it has to be whether it could go on a flexor substrate or a rigid substrate. So we wanted to consider these two alternatives. So this is what we want to explore. I want to see how we can do this inside SOLIDWORKS, and so inside SOLIDWORKS we're going to show you how we can build these models and work with multiple configurations and do simulations and explore the antenna parameters of these alternative configurations and design approaches. So we'll see a case where we would consider a flat antenna placed on a flat part of a bracelet, and what happens if you curved that antenna and placed it on a curved part of the bracelet. So that's really the goal of today's webinar is to cover these alternative design scenarios and how we can get these results and compare them. Okay, so now I'm going to switch to the software. So we're going to go and switch to SOLIDWORKS. So here you can see inside SOLIDWORKS I have built a complete model where I have actually a model of a hand. I have a bracelet model, and we have an antenna model. Okay. Now these antenna dimensions and the model were preset, pre-calculated ahead of time, and just illustrating to you that within SOLIDWORKS, okay, you could be working with this entire configuration. Somebody from maybe an arts department or something can be working on the looks of this and designing this, and the antenna engineer is really interested in this, in the antenna part of this. Okay, so this is inside SOLIDWORKS. This is an assembly, and SOLIDWORKS has these design tables which allows us to create, with these different parts, create different configurations. So you can see here I have essentially 4 configurations. I have a configuration for the flat antenna, which will be the antenna of interest for me. As a designer, I'm going to focus on the antenna part. What I'm showing right now, which is active, is the antenna when it's placed on the flat section. So that's my current configuration. If I want to see an alternative configuration, always within the same design, I can just show this second configuration. And this configuration, you notice that we placed the antenna on a curved section. So now my antenna is curved, okay? And then if I isolate the curved antenna, I can have that in a separate configuration. This is my curved antenna design, okay? So this is what is accessible to a designer inside SOLIDWORKS. Obviously, you can have complex assemblies and so on, and you can have a configuration which focuses on the part of interest to the designer, what you're trying to solve. Okay. So now, among these designs, obviously, for simulation purposes, we're going to be using HFWorks to study the parameters, see if this antenna design will fit our needs or not, and if we have if we meet the specs in terms of frequency, polarization, and all of those things. Okay. So to do that, you'll notice here that what I mentioned earlier, HFWorks is an embedded product inside SOLIDWORKS. So HFWorks is this tab here, and it's also accessible through the tools menu under HFWorks. So you have a whole bunch of menus, a whole bunch of options under the HFWorks menu here. HFWorks also comes with its own manager toolbar. Okay, so you can, a bunch of commands you can execute straight from the toolbar. So the idea that we wanted, and again, we're not going to go over the geometry. Suffice it to say that for those who know SOLIDWORKS already, this will be the geometry generation part should be relatively straightforward. For those who don't, SOLIDWORKS offer a lot of tools, videos, tutorials, and so on to bring designers up to speed. And because it is such a popular product, it really has a lot of resources, and it's made to be easy to use and to be productive for designers. So a design shouldn't take you too long to build. Unlike packages that do their own geometry editors, we don't do that. We really leverage the full power of SOLIDWORKS, and you've seen right off the bat that we can do multiple configurations. We are actually doing multiple designs in a single geometry file. So the process of getting simulations in HFWorks is we call it studies. Every scenario, every simulation is a study. What we see here is the name of our assembly. It's called Bluetooth antenna. And under the assembly, there are different configurations. So if we wanted to study this antenna, we would create a study. Okay, and by creating a study, we can do different types of simulations. So in this case, we're interested in an antenna simulation because we're going to get antenna parameters, and we can set different properties of the simulation, the frequency range, some other properties, what we want to do in terms of whether it's discrete or fast sweep, and a few other things that we can set. And we also decide that we want to compute the far field parameters. For antennas, we need the radiation pattern. So by default, we're going to compute the far field parameters with a certain resolution. So I want to give you a very quick overview of how this is done. how do we do this simulation, you will see that it's relatively straightforward. And I also want to highlight here what I mentioned about the thermal coupling. So if you want to do thermal coupling, you just turn on the thermal coupling feature of HFWorks. So if you were to do a simulation like this, okay, with that name, which is called Study 3, you see that it has a symbol of antenna to tell you that this is an antenna simulation. And right now I'm working with the bent antenna. So my simulation is going to be for the bent antenna. And then the process really of simulation is a 3 steps. We need to define the material properties. We have to apply the excitations and the boundary conditions, and we have to generate a mesh. Okay. The third step being optional, because the software can, when you can have the software auto create the mesh for you when you ask it to solve the problem. So the mesh, the material application process, it's standardized. We have a built-in material library. Okay, so here you have a whole bunch of different materials to which you can add your own material library by creating your new material library. So in this case, if I'm looking to apply a material to a substrate, I can expand the substrate. And if we're doing, say, a Rogers material of some kind, then we can pick the Rogers material. If we're picking some other supplier, then you pick that supplier and so on. Okay. So in this case, actually, as you can see, I applied my material, substrate material to the air, but I need it for the substrate. So I'm going to just drag and drop onto the substrate. I'm going to right-click on this one, and I'm going to apply material through my favorites, which is air. So I can change back to my air box. So this shows you that it's really straightforward and very flexible the way you do material properties and so on. Okay. Now to apply boundary conditions, since this is an antenna problem, okay, we need the first boundary condition we're going to apply is the radiation boundary. So we know that all the boxes, all the faces around this this antenna are going to be absorbing boundary conditions. This is a way of truncating the infinite space where the antenna radiates. Okay, when we cut that space, we create an artificial boundary, and it needs a special boundary condition, what we call the radiation boundary condition or an absorbing boundary condition. Okay, so that's where we apply the boundary condition. If we wanted to apply, let's say my conductor is going to be some kind of copper or something like that, I'm going to hide my air box. Okay, and I can select my copper, and I can go here and say apply. And this is not a perfect conductor, so it's going to be an imperfect conductor boundary condition. And I want this one to be the conductivity. Let's say this is made out of copper, then this would be a copper boundary condition, and you say OK. And so this shows you how the process works on setting up materials, boundary conditions, and so on. One of the things I would like to show to illustrate some of the useful tools for antenna designers. So whenever you're working with structures that have edges, metallic edges and antennas, so at high frequency you're going to have field concentration around the edges, and so the idea of meshing can be long if you wait for the program to do adaptive meshing and start with the mesh and keep refining. We offer something called mesh controls. And by applying mesh controls, what we can do is we can select the edges. So we can apply my mesh controls to parts, faces, or edges. And in this case, we want to do edges, but we don't want to pick them one by one. We want to pick them through a face. So we're going to select all this face, and then we're going to say extract edges. And on these edges, I want to have an element size. Let's say that's 0.1 millimeter. Okay, long. So what we've just said now, we said whenever we do the meshing, I want the mesh to be automatically refined to this 0.1 millimeter, and that should, for me, it could give me a mesh in one shot and get essentially the required mesh for accurate results. So we can do that with one shot. So then the mesh creation process is going to respect the global mesh size. You can have it coarse or fine or whatever. And then there are different options that we can set for the meshing. And if we ask it to create a mesh, it will automatically respect the global mesh size everywhere outside my controls area. And in the controls area, it should give me a mesh of smaller mesh size. Okay, so the process of meshing, as you can see, is automated. I could have bypassed this and had the software do the meshing for me. Okay, so you can see now that my mesher has respected my request that the mesh be refined around the edges of my antenna. And looking at this mesh, I can, with some training, for those who are not trained in high frequency electromagnetic, you can determine whether this mesh is good enough or not. And in this case, this is indeed a good mesh. So really, this is the process of setting this defining studies. Once we have done this, the next step is to run the simulation. So I've already set up a couple of scenarios. So let's see what our antenna does. If we look at the flat antenna, so we're going to activate this study, activate this configuration. So now we're going to look at the flat antenna configuration. Okay, so this is my flat antenna. I've applied the boundary conditions. So in this case, we simulated with a Rogers substrate. So this is an FR4 substrate with an airbox, and we had applied our port and boundary conditions. So we made some traces, a ground plane underneath. So we defined that as ground. We created the mesh and we solved. So you see that this study, your results are all grouped under this results folder. So the results have field, 3D field data for the electric field, 3D magnetic field data for the magnetic field. We have port results, and then you have a whole host of electric parameter results. So this includes stuff like S parameters, input impedance, radiation pattern, and the likes. The process. So if we look at the results table, then it's telling us in this case that our center frequency that we used is 2.45 gigahertz. Then we have these are my antenna parameters in terms of how much power is incident, how much is accepted, how much is radiated, and so on. It's also giving me how much return loss I'm having at that frequency, essentially to show that this is a pretty good match for this antenna. So this is tabular data that we can look at. Then we can do plotting of data in 2D, like XY plots, Smith chart plots, or polar chart plots. So in this case, we wanted to see what is the return loss of this antenna. We've already generated the return loss plot. So we can see that this antenna is centered at around 2.34, very close to 2.45 gigahertz. So this is my 2.45 gigahertz, and I have essentially better than 20 dB return loss. So this antenna is really nicely centered and has a good match over the, I would say it's better than 10 dB from this point, which is 2.29 to about 2.62 gigahertz. Okay, so this gives me some confidence in this antenna performance. Then if I wanted to see what its radiation pattern looks like, I can go and say a 3D polar chart in a fringe format. Okay, and you can see here that by default it's selected, it's showing me the gain pattern. If I want to change that, I can pick any other pattern that I want to see. Okay, and I can see this in 3D. I can play with the chart options and so on. But this is essentially showing me that essentially what I'm looking for is some omnidirectional coverage, and I'm seeing that very well. Okay, and I'm seeing that if I wanted now to cut this radiation pattern, if I want to look at it at theta equals 0, so I can do a polar plot, and I see that indeed that I have a very nice radiation omnidirectional coverage of this antenna. I can look at this data in listing format, so I can see how much gain I'm having. Obviously, this is not a high gain antenna by any means. It's a very miniaturized antenna, but it does respect the omnidirectional coverage that I was looking for. If I want to look at the cut of this in the phi plane, then I can see that this antenna is not entirely symmetric because the structure is not. And this is what I'm looking at in terms of radiation pattern in the phi plane. We can generate multiple plots in different planes and look at different things. Again, the VSWR, okay, definitely better than 2 over the band of interest. So I can see that this antenna is well designed. My flat antenna works. It meets the specs. If I wanted to do 3D field plots of radiated field and so on, I can do that as well. But at this point, I want to switch to the second one. Now the question is, what happens if this antenna, same kind of dimensions, but we just conform it, it becomes a conformal antenna and shaped in a bent manner. Okay, so this one, if we activate this this configuration, now we're going to switch to the bent antenna model, and want to see what impact does bending the antenna have on the antenna performance. Okay, so let me see here. Okay, all right, so now I can see that I have, so I'm looking now at the bent antenna, and because it's the active one, and this other study is also for the bent configuration, I can see that these two are active. Now I want to see what happens to the return loss, and now I'm actually, I have my original antenna, which is the flat antenna, which is in red, and when I bent this antenna, its match shifted, its frequency shifted slightly to the left, so it's a lower frequency match. Okay, so for all intents and purposes, if I'm looking at 2.45 gigahertz, okay, I can see that I have my antenna is still functioning. So without much additional design tweaking, I could say that if I place this antenna at 2.54 gigahertz, I'm going to get about 13 dBs or better than 10 dB return loss. So it's not bad. Okay, so the bending issue, as far as the matching goes, is not a big issue. If I look at the radiation pattern then of my antenna, again, the coverage is not affected that much. Okay, my antenna pattern is still by and large quite omnidirectional. I can double check that by looking at my theta plane. I have a little bit less gain than I had with the original antenna, but short of that, this antenna is still operating, and VSWR again shifted a little bit to the left, but still within the acceptable range. Okay, so this essentially shows us that I'm able to analyze alternative configurations, okay, within a single design environment with a single SOLIDWORKS geometry interface. Okay. My apologies. I think I actually think that, let me make sure that what I've just said is so we're showing the results for the bent antenna, and these results are as far as return loss. So we see that the original is in red, which is the flat antenna. The curved antenna is in blue, so I have a slight shift to the left. But still, when I look at the 2.45 gigahertz, I'm still better than 13 dB return loss. So again, my radiation pattern is not affected by that much. So if I look at my radiation pattern, it's still quite omnidirectional. If I look at a theta cut, I have about -11 dB, slightly less gain than the original antenna, but still performing within specs. And my VSWR is still below, essentially below 2 at 2.45 gigahertz. So I have 2.45. I'm about 1.5 of VSWR. So this antenna, whether we put it in flat or we put it curved, it's still going to work. So the key thing here is that this model, this circuit, this structure, this length, this kind of serpentine is going to meet my requirements and give me Bluetooth coverage for my wearable device. Okay. So this is what we wanted to illustrate in terms of how we use SOLIDWORKS and HFWorks for the design of antennas. This is intended to give you a short flavor of what the software does. Before closing, I want to just show you one additional piece of productivity that the product offers, which is the report generation. So if you've created a whole bunch of results and built the model and so on, you want to document that. The way we do this is by report generation. It's an automated report generator. It has a table of content that includes all of these elements. So typically you will have your company logo configured and your title and so on. And then you can generate this in HTML or in Word. And if we pick Word and have it shown inside SOLIDWORKS, so this gives you an idea what happens. You don't have to do cut and paste and print screen and all of that. It's all done for you, and it's all compiled within a single Word document. So you can see here that HFWorks has generated this report and brought it into SOLIDWORKS. And you see here, if I, since we are in Word now, I'm going to just zoom this to 80%. So this is my table of content. So if I wanted to go to my electrical parameters, I can control-click and go to that section of the document. So you have here your S parameter plot, you have your radiation pattern, different cuts of the radiation pattern that will generate VSWR plot. You have the port electric field and so on. And because it's a Word document, obviously, then you can edit and add comments and text and so on, and you can save it. And okay. All right. Okay. So I think that gives you an idea of what you can do. If you wanted, let's say, for the sake of argument, take this antenna and change something and resimulate, you can just drag and drop make a copy. So I can make a copy of this, and I could go and say, for example, if I were to use another material instead of Doroid, if I want to use Docapton, for example, for flexible substrate, that's relatively straightforward. All you have to do is you generate a copy of your study, and then you go to the materials, and then you edit your material, the substrate material. You can edit it, change its material property, okay? And then, instead of an epsilon of 4.5, you can say that this is an epsilon of 2.33, for example. And you say, okay, and then you can resimulate the structure. Alternatively, you can just go, instead of editing, you can go apply material and pick some other material, okay, some other substrate material, for example, and use that. Let's say some kind of Q-flan, for example, and apply that. And then it's gonna, you need to update this. You need to run again to update the results to take into account the fact that you're using different material. Okay, so I hope that we respected the time constraints for everybody. So let's see now if what kind of questions are out there, and try to address some of them. So, okay. So there were a couple of questions about the parts, human body parts models. So one thing I think that it's very interesting in working with SOLIDWORks is that there are at least two very good websites where you can find a whole bunch of pre-made models. There is a website called GrabCAD, and if you go to the site and you search for models, a hand model, a phantom model, or something, you can download those for free, and you usually find different formats. Often you will find the SOLIDWORKS native file that you can import. At the second website where you can find ready models is the 3D Content Central. It is a website by SOLIDWORKS itself, and there as well you can download ready models. They are usually made by the community, and they're shareable, accessible on free of charge typically. So so if you look at this is a website of GrabCAD, and you can see all kinds of models out there, so you can bring those in. So there are another question about the ports we have. How do we apply excite the structure? I kind of glossed over this. If you look at the boundary conditions, we can have a port. We can have a kind of what is more like a distributed port, or a port of a wave, or we can have a lumped port, which is more of a punctual excitation. So the port is really where you're exciting the structure. So we can support either of those two by applying the ports. In addition, you have all these other kind of boundary conditions that you can apply, including symmetry boundary conditions that can help you reduce the size of the model. Okay, and questions about the runtime, how long it takes to solve these problems. I'm demoing this on a kind of a standard laptop machine with about 12 gigahertz of RAM, and we can solve more than 1 million unknowns on this machine in probably the space of less than 20 minutes. So that gives you an order of magnitude. If you were, let's say, if I were to actually say, okay, I wanted to go and go to this configuration, for example, activate this configuration, and say I wanted to compute, because there was a question about SAR and about thermal. So if I wanted to do this, okay, I want to excite this antenna here, and I want to see the fields surrounding this and so on. Obviously, my problem is going to become larger because I'm going to have a bigger mesh. But there is intrinsically no limitation in the software that would prevent you from doing that. And we do actually do computation of SAR so that you can plot the specific absorption ratio or absorption rate into the human tissue and see how much of radiation is penetrating the model. The time that would be required in that case obviously expected to be longer, and you might need some additional memory, maybe 20 or 30 gigabyte machine will allow you to solve bigger problems. The issue being that at 2.45 gigahertz, the wavelength is about, let's say it's about 10 centimeter, around the 10 centimeter range in air, but in the human body with high dielectric, so the wavelength becomes smaller. So if you make the bigger your model, the more mesh you're going to need, and the more it's going to take time. If I were to do that problem personally, I would probably just section off a section of this model, maybe focus around the wrist and around the the bracelet, and see how much field is going to penetrate, because really you expect that your highest field intensity is going to probably be right around the area underneath the antenna. Keep in mind that this antenna and the bracelet can have a ground plane that's going to isolate the body from the antenna. But in other applications where you might actually be using, designing some wearable to apply microwave energy, like for ablation purposes or for whatever, then of course you need to model the human body, and you need to apply the antenna directly there. So the software is able to handle all of these scenarios. The runtime is, typically, like I said, if you're about the million and a half unknowns, you are under the 20-minute runtime period. Let's see if there is any additional questions. Oh, that is okay. A question about tuning. So the tuning per se, because the tuning of S parameters is it's really through multi-configuration, or it's also can be done through. Let me activate this. Show this configuration. Okay. And if I wanted to go here, okay, and let's say I'm going to define a new study, and let's say I wanted to see how I can tune certain parameters with geometry, then I can do an antenna, and I could tick off here parameterization, and parameterization allows me to put in different values of a given dimension. Let's say if I want to play a little bit of the line width, for example, or the substrate height, or a combination thereof, I could do that through the parameterization, okay? And so if you'll see that if I create this study with parameterization turned on, then I can go and right-click here, and then I can say go here and say, okay, which dimensions do I want to parameterize? So I can go to my SOLIDWORKS and then open, let's say, my substrate, and say open this feature. Double click on this sketch, okay, and in out of that sketch I can pick the dimension that I want. Okay, so let me see now. This one is in the way, so I can click a dimension and say, okay, this is I want to change this dimension or drive this dimension, okay, I need to pick the right dimension here to illustrate how do we. I think this one is the outer dimension, so I need to look at the strip itself where I have the split lines to change. But the idea is really I can pick the dimensions from the SOLIDWORKS assembly drawing, and then I can parameterize those, and that would be a way to do this kind of tuning or search for a better design. Okay. Any other questions? Someone is asking if they can be a presenter. We cannot do that, but if you have specific questions, maybe you can type it in and we can see if we can answer it. Okay. So I'm going to exit the edit component. So I think this pretty much